Okay, cotton parametric modeling demonstration using Revit system. Let's take a look at this case, okay? For the first case, I like to introduce you how to make custom object in using Revit, the first one. Actually, not the Revit. Revit is not the only one sole option in BIM tools. Actually, there are more tools. Those examples have done 11 years ago by me at Georgia Tech. Okay, 2005, I made those examples with my colleagues. The purpose was to present this slide to local architects at the time. Local architects at the time, architect firms, SOM, HOK, Parkinson and Will, and so on, okay? They came to Georgia Tech Digital Building Lab, and we introduced them how to create custom parametric object using cotton examples, okay? This one is Revit example. Second one, example number 2 is same object, but Bentley system, Bentley architecture. Actually, I was in charge of making Bentley system. This one done by my colleague. But anyway, just for your information, let me show you demonstration, okay, example. Okay, take a look. Interface looking very coarse, simply because this is, I told you, 11 years ago. Very early version of Revit. At that time, the program name was Revit Building, okay? Revit Building. Revit Building version 6, 5, 7, I don't remember. But anyway, 2005, we used the Revit Family Editor. When you create something in parametric tool, you have to think, okay? You have to plan the process. Firstly, physical shape modeling, and then parametric modeling, some constraints which enables us to use this one to any surface, any assembly, okay, any design project. So by using Family Editor, defining section profile, elevation first, and some equations, constraints, formula, to create 3D solid as a part, okay? This part now has width, height parameter, and they can be loaded into this project. So if we have part 1, 2, 3, part N, they have parameters linked together with constraints and make an assembly. Part 2, 3, all other parts can be loaded to same project, same assembly. So width and height of a part, width and height of the assembly. Number of array to width direction and number of array to height direction. At the end, this kind of shape created as an assembly, okay? So let's take a look at this case. This is Cornier's real product. Cornier company really manufacture and install this truss wall system. So this building design is very roughly made design just for demonstration purpose. So take a look. This is cotton wall system, some arc-shaped wall. And this Cornier truss wall system defined by Revit Family Editor in this way and installed to this assembly surface like this way, okay? Height and number of vertical mullions. So installing this truss wall system in Revit project like this way, okay? Making its height, appropriate height, and the geometric shape, followed by the arc line. So this is the Revit render output 11 years ago, okay? Another render from interior. And next example, we'll see after the break, okay? Let's take a look at second cotton wall example, number 2. Parametric modeling demonstration. At this time, not Revit, it's Bentley architecture, okay? In parametric modeling world, there are really high performance system named CATIA, nowadays Dassault systems, and Gary Technologies made some custom application named Digital Project, CATIA base. But there is another one, Bentley system, GC, okay, generative components. That is the Bentley systems parametric modeling tool, very complicated, some script language based parametric definition and very, very powerful tool. But anyway, 11 years ago, I was in charge of Bentley system. So let me show you some little bit more detail about this Cottonelle system, how to define in parametric way. Okay, thanks to my colleagues, Revit Family Editor and others all have done by at that time Georgia Tech Digital Building Lab. But this is Bentley example. Okay, at first take a look. Cornell 2800 truss wall system. Okay, this one has front mullion and rear mullion and horizontal frame, okay, mullion, and window system, window panel, and there is a web, okay, moon cut, half moon cut web to connect front and rear mullion system. So this is section profile, okay, in very detail, for manufacturing system, and this is elevation. So at first, plan how to make this one in parametric way. Component-oriented approach for 2800 truss wall system. At first, basic section profile in plan geometry. Next one, front and rear mullion, their assembly, front and rear, and the connection web, okay, web geometry. So all they loaded into one of the main part. Actually, this is assembly, okay, assembly from those subcomponents, but this is still a part, okay. This part can be joined with another section profile, other section profiles. For example, horizontal mullion and webs, connections, and wall surface. So this is final component, final project. What if you want to define arc wall or some curve wall, any different type of shaped walls? And then this one going to applicable to different assemblies like this way. So this is fundamental component-based approach for defining parametric model. So let's take a look. This is front mullion. Front mullion's height can be defined in this way, user input, okay? How about rear mullion? Exactly same to the front mullion, okay? And then you don't need to touch rear mullion's height. What you need to control is front mullion's height, one user input, okay? And then you can control like this. Secondly, you need to put distance constraint for this web distance, okay? So you can control with specific numbers or mouse click, and then the number of webs can be defined automatically like this way, okay? Next definition is the angle of installation. If the angle is 0, this one going to be looking like this, okay? But usually we have the angle. But this one should be flat. Why? Because this is, of course, a glass panel, okay? Bending glass, too expensive, okay? So that is why we have to always use flat glass system, okay? So flat surface, but angled. They are looking totally freeform, okay, in some distance. Anyway, they should be controlled by user input, but they all something relative, what if you want to control this one only and all others have equal to this angle, and then they can be controlled in easy way, okay? So if you change the angle or height relation, you can get this kind of equations, and you can get some angled horizontal mullions and so on. Let me show you one minor but critical example when you deal with this kind of parametric definition. Take a look, this horizontal mullion. This one has angle cut, okay? If this horizontal mullion always 90-degree cut, in this angle, there should be some gaps, okay? That kind of gaps sometimes make some unstable problem, structural problem, or some leaking rains, whatever, some problems. Anyway, we need to cut exactly based upon angle, okay, of this component. So how to resolve this problem? How to make proper angle cut for this horizontal mullion? That was the question according to this angle. So actually, in this kind of representation, it looks complicated, but just a middle school level mathematical definition, okay? Middle school level equations. So length can be defined A, B, C, and D. They all equal. Angle can be defined A equal B, and C equal half of B, okay? A, B, and C. So what if the angle arrow, angle A dash is kind of very narrow. In that case, angle cut going to be narrow. What if A2 dash wider angle? In that case, angle cut going to be kind of bigger. So all the equation totally based upon this. So in the definition, this is the shape definition of horizontal mullion on top view. So this angle can be defined in this way. Okay, unfortunately, this angle defined in this way, okay, counterclockwise. So if we make 10 degree, this one going to be 350 degree. That is why we need to put this kind of equation. But anyway, A1 length all relatively defined from one single user input, this one, this angle, okay? And then we can control the length according to precisely defined angle and the mullion angle cut, okay? So this is the preview of the final assembly component, Windows installation, and installed, followed by this arc wall system. So length, angle, diameter, coincidence, sweeping along paths, all parametric constraints and features used in this Bentley system. So this is kind of property view, how many components and their angles listed, defined in this way. So this is project view, something like Revit's project view. This is Bentley system 11 years ago, and some brief visualization for this real installation, okay? Let me quickly show you a demonstration video, okay? The reason for this video presentation is this one is same approach to the Revit family editor and Revit, but totally different interface. This is Bentley system, okay? Parametric Cell Studio at the time, something similar to generative components. Take a look. Front height, user input, and rear height exactly equal to the front one. But if you type your user input, that one going to be changed like that way, okay? So undo that and go back, same to front one. At this time, change front one to 20, and then rear mullion also changed exactly same to the front one, okay? change 20 to 15 and equally changed the rear one and change the view, right view. And at this time, click the mullion web and it's constrained. Take a look. Basic distance and the last point distance predetermined. Okay, so if you change the gap, mullion gaps will change. But this one has some structural problem. So if you change the gap from starting point shorter than before around here, and then a lot of webs going to be installed in automation like this until the end point. Okay, this is fundamental approach of parametric modeling. Okay, next example will show you its installation, physical installation, horizontal mullion. So all data path definition, and this is solid object. So clicking path and starting point and simply follow by the path line, and then this one automatically cut by the equation that I show you in the slide, and all the horizontal bars going to be installed like this way. Okay, this is sort of parametric approach to define this structure. Take a look, angle cut or well formed and installed based upon this user input for this one. So installed and measured, okay, until the end point. Okay, the third example will show you the final assembly. Okay, this is the top view of installation. So if you click the angle, the first angle value can be defined. Actually, this is 3D view like this. Okay, just no windows installed. But anyway, frames, mullions all installed. But in top view, we can now control the angles. So take a look. The first one angle has 350, and the second and third one all exactly same to the first angle. Okay, that means if you just change the first angle, all others accordingly updated. So if I change 355 and then 3D model going to update total exactly same to 355, except this part. Okay, this one has some different definition. So this kind of modeling approach already demonstrated in this way 11 years ago. Okay, so actually this is not up to date and some cutting edge, but I think this example is good to beginners for parametric modeling. And also today's lab exercise, you are in charge of making something like this using Cottonor system in Revit and Family Editor. For parametric design, parametric modeling, you have to think first, okay? Very important. Before mouse click, not only in a designer standpoint, but also in engineer's standpoint, okay? You have to define your geometry in engineer standpoint or mathematics perspective, okay? I mean equations. This one should be equal to this or half of this or some kind of sine curve, cosine curve or tangent, perpendicular, 90 degree, orthogonal, whatever it is, you need a plan, okay? Without plan, you cannot define anything. It's just a geometry done by 3D Max or SketchUp. So that is why parametric modeling sometimes, at first, especially at first, it's very looking hard, difficult. But we have to get this, okay? Okay, so far we have walked through how to use BIM approach for your design. You know how to model this building, roughly, okay? Also today's lab exercise, you are in charge of making some finalized building design, including some interior design, ceiling design, lighting design, and so on. But the problem is, what's next? So far, we have learned Revit-based, BIM-based design, but actually, in terms of BIM and application, that's just an initial point of BIM application. There are amount of unexplored world in BIM and applications. BIM-enabled design done by architects, done by designers, that's just start point of building information making, okay? How to use such information, how to apply those collected information for what? For construction, for maintenance, for management, for better design, whatever, okay? So what can I do for better design? We do design using Revit. What's next? Let me show you some brief cases, okay? Some examples that I have done or now I'm still working on, okay? The first one is Georgia Tech's digital building labs, US courthouse design automation, okay? At the time, around 7-8 years ago, very famous architect firm, H3, Parkinson and Will, or some other companies, designed US federal building, federal government building, courthouse. United States, very huge country. So in every year, in average, 7 new courthouses planned and built, okay, every year. So 7 courthouses per year in average. Anyway, when architect design courthouse, design alternatives using Revit or any other BIM tools, we got Revit model, IFC model, and analyze space program, circulation and security, energy analysis, and cost estimate, several ways. And then we suggest which design is the best option for this courthouse, something like that, okay? Let's take a look at some more examples. This is one small example of this kind of design analysis. The first one is area calculation. Take a look. This is room object in Revit. Its area is here, 189. This area computed by internal walls area. But you have to know that there is wall. How about wall, construction walls area? Center line of the wall returns this area, okay, 201. But actually there is standard, NC BOMA standard. BOMA means Building Owners and Management Association. In terms of their definition, some walls should be used for internal line, but some side, center line, something outer wall, okay? Very complicated, even by human, very time consuming and complicated. But thanks to BIM application, we can make this kind of precisely measured area, usable area, okay? This one looking very small difference. What if thousands of spaces in a building, several thousands of square feet different, okay? Why it's important? Leasing fee, okay? How much money you have to pay for this area? 1,000 bigger, smaller? Money is different, okay? That's why it's critical. So this kind of application we developed. And this is Space Program Review Report, Excel file. This one doesn't written by hand. I mean, it's not manual. Automatically generated Excel file from BIM tools, okay? Auto-generated. Revit and BIM tools know how many courtrooms, how many office area, how many parking space, building ratio, how many elevators defined in this building, and make this kind of Excel report comparing two concepts, two designs, okay? We can compare two designs. This is Art1, Art2, okay? So easily compare by numbers. Circulation checking using auto-generated graph. Number of tons, working distance, spatial depths, height, area, visibility, all they are measured and counted by computers from specific space to other space. Very detailed. So also analyzed circulation and security. This is sort of security analysis example. In courthouse, there is restricted zone for steps, attorney, judges, public zone for public, and secure zone. Secure zone means, you know that in US drama, some prisoners with FBI or US Marshal, very securely handled corridors, circulation paths. They all separated and secured, controlled. We can take a look. It's correctly defined or some problems. For example, public secure or even restrict secure, they don't overlap each other. That's the rule, okay? So we can review in this way. And also energy analysis, as well as circulation visualization analysis. For what? For choosing the best option among various design alternatives. So all they are looking something coarse, but they all Revit model, okay, at the time, 2008. Revit models several design alternatives, but at the end, this design selected because this one has most efficient and most secured, no problems in circulation, and so on, okay? And the committee picked this design for real construction for Ohio State, Toledo City, okay? So that's probably constructed. Okay, so far we have reviewed some examples. Before getting started lab exercise, let me quickly show you another case in detail. Okay, in today's lab exercise folder, you can find out data Revit application. Let me show you this presentation quickly, okay? Simply because this one's, take a look, this model. What is this? This is our building, okay? College of Human Ecology building. By using BIM application as an extension of BIM, this one designed by Revit, okay? Intentionally. So how to use this BIM model for better design? Let me show you one example, one case. This one done 2014, represented in international conference done by my graduate students. Take a look, demonstration of BIM-enabled quantitative circulation analysis using Bera language. Bera language is BIM-enabled scripting language for doing something like this. Okay, some background and some slides simply shows you design review is very time consuming and critical for better built environment. So by using BIM, we can take advantages of quantities, okay, numbers we can get from the building. This is our building, okay, College of Human Ecology building. 3 colors, which means food and nutrition, fashion, and interior architecture design departments, 3 departments. How to allocate, how to make special program for better layout, better efficient circulation, and so on. So we reviewed by using numbers from BIM model, okay, quantities. So circulation, special program review, and so on. So we made some BIM-based mechanism for design review using better language and returned output. Anyway, at the end, take a look. We made some mechanism for analyzing circulation and special program. This is our floor, okay, level 5, library and computer lab. So this one can be analyzed in terms of circulation. This is auto-generated graph, okay? So thanks to this graph, we can get how many spaces, how long distance we have to walk for entering or exiting the space, and so on, okay? So we can get average walking distance for interior architecture department, average working distance for fashion department, average distance or total distance for food and nutrition department. Of course, they are located below floors, so comparatively short distance, but we don't know how much. So this one exactly returns the numbers. So this is the picture of the reconstruction. Based upon this query, we can get some numbers, okay? So this is the final number, okay, for the design alternative 1 and 2. We can easily compare those two design alternatives. Accordingly, this one looks something efficient or short working distance, a little bit short. It doesn't mean that this one is good design, but we can figure out how many or how much numbers different from those different alternatives. Formally, in conventional CAD approach, if we have many design alternatives, how to determine which one is better? Just to take a look, and we have to depend on some architect's knowledge or their speech or their something special, unknown, black box knowledge, okay? But thanks to BIM, we can visualize like this using chart, design alt A, B, C, which one has longer distance, average distance, total working, was the shortest and the longest, and so on, okay? We can easily compare them. For 3 departments and entire passengers, working distance, and so on. Okay, this is a brief overview for the BIM application. Let's move to the lab exercise.